Hello everyone, I am Thomas Yuki from Kawada Technical System, Japan. I would like to talk about data management methods for a 3D product model in graph database. These are contents of my presentation. To start, I will talk about the background of our research, especially about sharing information of BIM. Generally, industry foundation classes is used to describe 3D product model with BIM. Many 3D CAD can be imported and exported as IMC data. IMC code attains ISO by using Smart International. IMC data is very popular for sharing product models. This figure shows the maturity of BIM. As the maturity level increases, the method of sharing information also evolves. Using papers, using files, using library, using integrated web system. Currently, even the most advanced countries using BIM, the UK and Finland, no country has achieved level 3 yet. So all of us are aiming for an integrated system on the web. However, IMC data is very large and has a very deep hierarchical structure. So the below programs will make it difficult for us to reach the integrated web system. First, it's difficult to share the product model on the internet because the amount of data being transferred is massive. Second, a relational database cannot efficiently manage IMC data that has a very deep hierarchical structure. The figure on the right shows that the slowdown is enormous in relational DB when hierarchy levels increase. On the other hand, such slowdown won't occur when using a graph DB. Therefore, we decided to use a graph DB in our research. The aim of this research is below. First, store the IMC product models in a graph database, which is classified as NoSQL, to manage the models efficiently. Second, extract a portion of the models in the graph DB in order to reduce the amount of data transferred and network transfer time. Next, I will explain GraphDB. GraphDB is a database management system with create, read, update, and delete operations working on a graph data model, which is called property graph model. Unlike other databases, relationships take first priority in graph databases. The figure on the left is a directed graph in graph theory, and the figure on the right is a property graph model of GraphDB. The property graph model can have one label and any properties within every node and every edge. The NemoJDBMS that we are using in this research has the ability to traverse 1 million nodes per second. It's necessary to convert the IMC data to the property graph model in order to store the IMC data into GraphDB. I will describe how to convert the IMC data to the property graph model. If we convert instances into nodes and the relationship between instances into edge, a similar structure to the graph on the right will be created. In the property graph model, the entity name becomes the label of a node and the attribute name becomes the property of an edge called name. If IoT data has instances indicating a relationship between other instances, these are converted to edges instead of nodes. Therefore, this rule makes it possible to represent the relationship by only one row of direction, and to improve performance of traversing the graph. If the related instances are aggregated, each node is connected at an oriented edge which has the name and the index properties towards the node. If the instance attribute is a single data type or enumerated data type, store the attribute value by creating a property with the same name as the attribute name in the node. Finally, this property graph model is an example of what you can expect when using our method. All information of original IoT data is contained in the graph. Next, I will describe a partial extraction method in GraphDB using an example in which we extracted shape representation data from a door on the second floor of a building. Those nodes shape representation data. Order of the methods are below. First, select a target project based on its name. Next, select a special element from the condition. Next, select a component from the condition. Finally, extract all shape representation data from the component in step 3. To continue, I will explain the details of the extraction method. This process means an entire building is gradually narrowed down to the shape data of a component. Also, the number of nodes traversed by DB decreases. Therefore, a GraphDB operates more efficiently. Next, I will talk about the verification of the partial extraction method. Our procedure is below. First, use our Java program to store an IoT data of a building into the Neo4j DB. Next, execute a partial extraction query. Then, surface IDs and coordinates are exported in a JC3 format file. Next, scan surfaces and coordinates from the results of executing the query. Then, use our Java program to convert CSV data to OBJ format, which is a very simple 3D model data format. And OBJ data is exported. Finally, we will shape representation of the result using OBJ view. Target data of extraction method is right of stairs on the right. The image on the right is close-up of the fifth floor of the building on the left. The purpose of this verification is to extract the flight of stairs from a 5-story building. The building is made up of about 1 million instances. The max hierarchy levels is 19, and the average hierarchy levels are 11. Also, flight of stairs contains 13,000 surfaces and about 40 vertices. I will show you a query used in this verification. What we include parametric information. Each line of this query is generated based on every parameter and put together at the end. This very simple query can extract shape representation data from a specific component on a specific floor of a specific building. Then we got these results of the verification. A result for counting surfaces and coordinates are shown on the table below. And the result for viewing the shape representation of the result was a figure on the right, so we can see that the results were correct. Conclusion of our research is below. First, the RC product models can be converted to property graph models through the below rules. Converting entities to nodes of a graph and connecting nodes related to each other by graph edges. However, an entity indicating a relationship of IFC is converted to a graph edge. Next, we developed an algorithm to extract paths from a graph database storing RC product models. However, there is not enough research regarding the general use of the algorithm. Finally, we were able to extract shape representation data from IFC product model by using a very simple query. It suggests that the integrated web system of BIM can be developed easily using GraphDB. We would like to continue the research of GraphDB and achieve the things below. The partial update of Archidata and optimizing the query for higher performance. Implementation of changing histories property graph model. And generalizing an algorithm for extraction that can deal with various conditions. Thank you for your attention.
Thank you very much for your interesting presentation. Any questions, please?